Every electric car you see on the road today is built on a lie. Not a marketing lie, not a PR spin, a chemical lie, buried inside the battery itself. Something engineers have known for 30 years, something the entire industry quietly accepted because there was no alternative. There still is not. Not yet, but in 3 or 4 laboratories around the world right now, that lie is being dismantled, completely permanently. And when it is, every EV on the road today becomes obsolete overnight. To understand why solid-state batteries matter, you need to understand how we got here. And that story does not start with Tesla. It starts more than a century ago. The earliest electric vehicles ran on lead, acid batteries, heavy, slow, brutally inefficient, but functional. In the early 1900s, electric vehicles actually outsold gasoline-powered cars in the United States. Then the internal combustion engine arrived, fuel infrastructure expanded, and EVs were pushed to the margins of history for nearly 100 years. The next meaningful leap came in the 1990s with nickel. Metal hydride, MIMH Toyota, built the original Prius around it. Lighter than lead acid, more energy, dense, more reliable. It worked well enough to launch the hybrid era. But MIMH had hard limits: energy density too low, self-discharge too high, and temperature sensitivity that made it unsuitable for a true long-range electric vehicle. Then came lithium-ion. This is where the modern EV story actually begins. Sony commercialized lithium-ion chemistry in 1991. Originally for consumer electronics, laptops, camcorders, early mobile phones. The chemistry was a genuine breakthrough. Energy density far higher than anything that came before it. Rechargeable hundreds of times. Relatively stable under normal operating conditions. By the mid-2000s, engineers began asking a different question. What happens if we scale this up to a vehicle? Tesla asked that question more aggressively than anyone else. The original Roadster, launched in 2008, was built from thousands of small cylindrical lithium-ion cells, the same format used in laptop batteries, wired together into a single large pack. The approach was unconventional, borderline improvised, and it worked well enough to prove the concept. Long-range electric vehicles were not just theoretically possible, they were buildable. The rest of the industry eventually followed, slowly at first, then with enormous speed and capital. By 2020, lithium-ion had become the universal chemistry of electric mobility. Volkswagen, General Motors, Hyundai, BMW, Stellantis, every major automaker was reorganizing around it. Gigafactories were rising on multiple continents. Global supply chains for lithium, cobalt, nickel, and graphite were being locked in for decades. The physical infrastructure of an entire industry was being cemented, literally and figuratively, around a single battery chemistry. And that chemistry had serious problems. Several of them. The core issue is this: lithium-ion requires a liquid electrolyte to function. A solution, typically a lithium salt dissolved in an organic solvent, that acts as the medium through which lithium ions travel between the anode and cathode during charge and discharge. Without that liquid, the electrochemistry does not work. But that liquid is flammable, it degrades, it behaves erratically at temperature extremes. And at a fundamental level, it limits how much energy you can pack into a given volume and weight. The industry knew this. The answer, for decades, was always the same: manage it. Engineer around it. Add thermal systems, safety layers, monitoring circuits, structural enclosures. Add complexity to compensate for the chemistry's instability. What nobody seriously asked until recently was whether the liquid could simply be removed. The physics problem at its most basic level: a battery is an electrochemical engine. It stores energy not as raw electricity, but as chemical potential. During charging, lithium ions are forced to migrate from the cathode, typically a metal oxide compound, through the electrolyte, and embed themselves into the anode, which in virtually every EV on the road today is made from graphite. During discharge, they travel back. That ion movement is what generates electrical current. Straightforward enough. But here is where physics starts to impose limits. Graphite can only hold a finite number of lithium ions per unit of volume. Its theoretical maximum energy density sits at around 372 mAh per gram. That number defines a ceiling, a hard materials, level ceiling, that no amount of engineering can push through. You cannot optimize your way past atomic structure. The best lithium-ion cells available today, including the ones inside a Tesla Model Y, a BYD Seal, and a Hyundai Ioniq 6, achieve somewhere between 250 and 300 watt Hors per kilogram at the cell level. Already impressive. But at the pack level, once you account for the thermal management hardware, the structural components, the cooling channels, the wiring, the containment systems, that number drops. Sometimes, to as low as 160 watt, Hors per kilogram. That gap is not an engineering failure. It is the inherent cost of safely managing a liquid electrolyte at scale. You pay for the liquid's instability in mass, volume, and complexity. The liquid problem: the organic solvents used in standard lithium-ion electrolytes, compounds like ethylene carbonate and dimethyl carbonate, are not mildly flammable. They are highly flammable. And under conditions of mechanical damage, extreme heat, or rapid overcharging, they do not simply catch fire. They enter thermal runaway. Thermal runaway is a self-accelerating chain reaction. Heat triggers decomposition. Decomposition generates gas. Pressure builds inside the cell. That pressure causes structural failure, which releases more flammable material, which generates more heat. The cycle is self-reinforcing and, once initiated, extremely difficult to stop. The videos are not hard to find. Vehicles burning on highways, cars reigniting in parking structures after appearing to be extinguished, fires that conventional water cannot put out, that burn at temperatures exceeding 1000 degrees Celsius, and that can reignite hours after they appear to be fully arrested. Firefighters dealing with EV fires have sometimes had to submerge entire vehicles in open water tanks for multiple days to fully contain the reaction. This is not a manufacturing defect. This is the chemistry behaving exactly as physics predicts when conditions deteriorate sufficiently. Every lithium-ion battery pack, in every EV currently on the road, exists within a certain risk envelope defined by that underlying chemistry. The industry's response has been sophisticated containment. Battery management systems that monitor cell voltage and temperature thousands of times per second. Liquid cooling circuits running between cells. Structural enclosures engineered to redirect thermal events away from passengers. These are real engineering achievements, but they are also, fundamentally, workarounds for a chemical instability that was accepted from the beginning. The degradation problem, the third problem, is quieter than fire, but it is just as consequential and far more universal. Every charge-discharge cycle slightly degrades the liquid electrolyte. More critically, lithium ions do not always embed cleanly into the graphite anode. Sometimes they deposit on the surface instead, forming tiny metallic lithium structures called dendrites. These grow with each cycle, accumulating over time like slow-motion mineral formations inside the cell. Eventually, dendrites can bridge the separator between anode and cathode, causing an internal short circuit. This is why your phone battery noticeably loses capacity after 2 years of use. This is why EV batteries gradually lose range after 80,000 or 100,000 miles. And this is why the automotive industry treats a battery pack as a depreciating physical asset, not just in terms of dollar value, but in terms of actual electrochemical capacity. A typical lithium-ion EV battery retains roughly 80% of its original capacity after 1,500 to 2,000 full charge cycles. Under real-world driving patterns, one full charge per day, that translates to roughly 4 to 6 years before noticeable range degradation sets in. Which means a vehicle purchased today will measurably lose performance before most buyers have finished paying for it. The liquid electrolyte is not just a fire risk, it is a countdown clock, built invisibly into every EV ever manufactured. The idea that changes everything: remove the liquid. That is the entire premise of solid-state battery technology. 3 words. Deceptively simple. Extraordinarily difficult to execute at commercial scale. Instead of a liquid electrolyte, that flammable, degrading ion, conducting solution, a solid-state battery uses a solid material to perform the same ionic transport function. A ceramic, a glass, a polymer, or a sulfide compound that moves lithium ions just as effectively as the liquid did, but without any of the chemical instability that has defined lithium-ion chemistry for 3 decades. And here is where the cascade of consequences begins. Because removing the liquid does not merely solve the fire problem, it unlocks a fundamentally different battery architecture. One that changes the energy density equation, the degradation equation, and the long-term durability equation simultaneously. This is not an incremental upgrade. It is a platform change, the architecture shift in a conventional lithium-ion cell. The anode is graphite. We have established why that matters. Graphite's theoretical energy ceiling caps everything built above it. But graphite was never the first choice anode material. It was the safe choice. The compromise engineers made decades ago because the superior alternative, lithium metal, was simply too dangerous to use in combination with a liquid electrolyte. Lithium metal as an anode material is electrochemically remarkable. Its theoretical energy density is 3,860 mAh per gram. Graphite's is 372. That is not a modest improvement. That is a tenfold increase in theoretical anode capacity. The reason lithium metal anodes were abandoned in early battery research is exactly the dendrite problem described earlier. In a liquid electrolyte environment, lithium metal surfaces grow dendrites aggressively, far faster and more dangerously than graphite anodes do. The short-circuit risk was too severe for any commercial application. In a solid electrolyte environment, the physics change. A sufficiently dense solid electrolyte physically suppresses dendrite growth. The solid material acts as a mechanical barrier that prevents lithium structures from propagating across the cell. What was previously too dangerous becomes manageable. What was theoretically possible becomes practically achievable. Pair a lithium metal anode with a solid electrolyte and a high-voltage cathode, and you have a cell capable of reaching 400 to 500 watt-hours per kilogram. At the pack level, because solid-state designs require dramatically reduced thermal management hardware, real-world energy density could reach 300 to 400 watt-hours per kilogram. That is roughly double what today's best lithium-ion packs deliver, double the energy in the same weight, or the same energy in half the weight. Either way, vehicle range, performance, and design flexibility change completely. The chemistry landscape, not all solid electrolytes perform equally. This is where the engineering becomes genuinely complex and genuinely competitive. 3 major material families are currently being developed simultaneously. Oxide-based electrolytes, ceramics such as LLZO, lithium lanthanum zirconium oxide, are chemically stable and inherently safe, but brittle and difficult to manufacture consistently at scale. Sulfide-based electrolytes, compounds containing lithium, phosphorus, and sulfur, achieve ionic conductivity approaching liquid electrolyte levels, but are sensitive to atmospheric moisture and require careful environmental controls during production. Polymer-based electrolytes are more mechanically flexible and easier to process, but currently perform well only at elevated temperatures, which limits their operating range for consumer vehicles. Each approach has major industrial backers. Toyota has invested most heavily in sulfide-based chemistry and holds more solid-state battery patents than any other automotive company, over 1,000 filings. QuantumScape, backed by Volkswagen, is developing a lithium metal anode paired with a proprietary ceramic separator. Samsung's DI is pursuing its own sulfide-based cell targeting commercial production by 2027. CATL, which manufactures approximately 37% of all EV batteries on Earth, is developing what it calls a condensed battery, a semi-solid architecture designed to bridge current technology and full solid state. This competition is not purely scientific. It is geopolitical. Battery chemistry leadership in the 2030s may determine which nations and which companies control the next generation of transportation infrastructure. The real-world numbers here is what solid-state technology promises in practical, measurable terms. Charging speed. Because solid electrolytes do not degrade under high current charging, the way liquid electrolytes do, solid-state cells can theoretically accept charge rates that would destroy a conventional lithium-ion cell. Laboratory demonstrations have shown charging to 80% capacity in under 10 minutes. Not 30 minutes. Not 2010. Longevity. Without liquid electrolyte degradation and with mechanically suppressed dendrite formation, solid-state cells have demonstrated cycle life exceeding 1,000 full charge cycles, with less than 10% capacity loss. Some laboratory results indicate 2,000 to 3,000 cycles is achievable, which would represent 2 to 3 times the usable lifespan of a current EV battery pack. Temperature performance. Liquid electrolytes lose ionic conductivity at low temperatures. This is the direct cause of the significant range reduction EV drivers experience in winter. Solid electrolytes maintain conductivity across a far wider thermal range, from -30 to over 100 degrees Celsius, without meaningful performance penalty. Safety. Without flammable organic solvents in the cell chemistry, thermal runaway as currently understood becomes chemically impossible. A solid-state battery pack damaged in a collision does not ignite. It fails, but it fails without fire. These are laboratory-validated benchmarks, not marketing projections. The unresolved question the industry is working through right now is not whether solid-state batteries work. It is whether they can be manufactured consistently, reliably, and at a cost that makes them viable in mass-market consumer vehicles. That answer is not final yet, but it is getting substantially closer. So what does this mean for the companies that currently dominate the EV market? The company has quietly built the largest solid-state battery patent portfolio on Earth, and has announced plans for limited production of solid-state battery vehicles by 2027, with full-scale deployment targeting 2030. Their stated internal target: 1,200 kilometers of range on a single charge, fully replenished in 10 minutes. Tesla has remained conspicuously quiet on solid-state. The company's current strategic focus centers on its 4,680 cylindrical cell format, a larger, more energy-dense lithium-ion cell that reduces manufacturing cost and simplifies pack integration. It is a genuine engineering achievement, but it is still a liquid electrolyte design, still graphite anode, still subject to the same fundamental ceiling. Elon Musk has publicly called solid-state manufacturing challenges extremely difficult, an assessment that is accurate. But difficulty is not impossibility, and skepticism from the current market leader is not the same as immunity from disruption. Volkswagen's investment in QuantumScape represents perhaps the boldest single wager in the industry. The startup has demonstrated a working lithium metal solid-state cell in laboratory conditions, achieving 1,000 charge cycles with minimal capacity loss. Scaling that to commercial production remains the central engineering challenge. But Volkswagen's financial commitment signals that this is a technology the industry's largest players take seriously as a near-term reality. And then there is CATL, a company that manufactures more than a third of all EV batteries currently in production globally. If solid-state technology matures and CATL is not positioned to lead it, the consequences for the company are existential, which is precisely why they are moving aggressively, and why their condensed battery architecture represents a deliberate attempt to be part of the transition rather than a casualty of it. There is a consistent pattern in the history of transformational technology. The dominant solution, the one that won at scale, the one that every factory and supply chain and business model was built to serve, rarely collapses from a direct frontal attack. It is made irrelevant from underneath by a quieter technology that fewer people took seriously, until the moment it became impossible to ignore. Lithium-ion did not conquer lead acid through brute force or dramatic announcement. It simply became better, then cheaper, then inescapable. Lead acid did not lose a battle. It became obsolete. Solid-state batteries are not arriving as a challenger to lithium-ion, they are arriving as its replacement. Not universally next year, not entirely by 2030, but the trajectory is no longer seriously in question. The physics are validated. Chemistry is converging across multiple independent research programs. The manufacturing problems are engineering problems. And engineering problems, given sufficient capital, competitive pressure, and time, get solved. The electric vehicle you could buy today is a genuinely impressive machine. It is also, in all likelihood, the last generation of a technology that has already been superseded in the laboratory. Even if it has not yet been superseded on the road, the next vehicle you purchase may still run on lithium-ion, but the one after that, increasingly, probably not. The battery that will define the next 50 years of mobility is not the one we perfected over the last 30. It is the one we are only now learning how to build. And the race to build it, the real race, with real consequences for companies, countries, and consumers, has already started.